Hello, good afternoon, everybody, and thanks to attend our fourth webinar organized by ProGold. We are happy that also today you are here spending your time with us. It looks that also today there are many people from Asia, so a special thanks to them that are here deciding to spend their time with us also if it is almost night time there. My name is Stefano Gagliotto, and I'm the Chief of Sales here in ProGold, already 20 years, and I will be the moderator today. I remind you that the webinars are 8. This is the fourth one. They take place every week on Thursday at 4 p.m. chat time. And we hope as well that you will attend the coming ones. The formula is always the same, a section of about 30-40 minutes for the presentation, and a second part about 30 minutes reserved to the questions that you are free to do anytime using the Q&A tool that you find the bar at the bottom of your screen. I remind you that you can find all the material, the video, and the presentation in our website in progold.com in the webinar section. The title of today's work is Hotspot, a Trip Through the Ambiguity. We often hear and talk about this critical problem. It is always coming out at the end of the process. That's why it's not well loved. The speaker will be Gisela Cepeda. She's graduated in chemical engineering, and she works here at ProGold as head of industrialization. So I think that we can start. I said all. I can pass the word to Gisela, wishing everybody a good listening. Gisela, you can go and break the leg.
Thank you. Welcome, everybody. As Stefano said, my name is Gisela, and today I will be talking to you about hard spots. The work we're presenting here today is based on a presentation that we did at the Santa Fe Symposium in the United States a couple of years ago, and the main goal of it was to create a handbook of defects, in particular around hard spots, and to talk a little bit about the causes and the possible solutions that we can have in order to avoid this kind of defect. So why hard spots in particular? If we go and see all the type of defects that we can find within jewel pieces, we realize that inclusions account for almost 40% of all the defects we have. However, a lot of people talk about hard spots improperly because they interchange the term hard spots when in reality we have inclusions. They are not the same thing. However, they are usually confused together because they share a common characteristic, which is called the comet effect. What is the comet effect? This is something that appears at the end after we have polished, and it is an aesthetical effect. What we have is an inclusion that is harder than the base material that we're polishing. So when the brushes come top the surface, they're pushing this inclusion, and it's just like a boulder on wet mud. When we are pushing it, the boulder is just taking with it all the material in front of it, leaving behind a streak that it's empty. This comment, as I said, is typical for both inclusions and hard spots, but the fact that we do not have it does not mean that we do not have the problem. So what's the difference between an inclusion and a hard spot? A hard spot has a metallic origin, can either be a metallic element or an intermetallic compound, while an inclusion is usually of non-metallic origin. In particular, it's very common to have a ceramic origin in this case. We can also divide these two defects into very big categories. In the case of hard spots, we have three macro categories: impurities, agglomeration, and segregation. While for inclusions, we have four macro categories, which are investment, oxide, graphite, and abrasive. So I'm going to start talking a little bit about the first macro category of hard spots, which are impurity hard spots. So the most common contamination that we have is when we have impurities from gold, in particular osmium. Osmium is a metal that belongs to the platinoid group, just as iridium, ruthenium, rhenium, palladium, and platinum. And it's very difficult to separate from gold. In fact, there is only one way to separate these elements, which is through electrochemical processes. We can also have contamination from other raw materials, but it is less common. When we have contamination from osmium, we have that it tends to be very regular in shape. So even if we see it with the naked eye, we can easily recognize it because it has a completely set of characteristics that sets it apart from other types of hard spots. And they're rather large in size. So how are these spots formed? As I said, we have these elements that are already inside a gold. These elements melt at a very high temperature, way higher than the usual temperatures that we normally use in our melting processes. So the particles are solid within the melted alloy. When we are having the solidification, these discontinuity points, these solid particles that we have inside, are the first points where the metal starts to solidify. They are called nucleon points. We have that all the solid particles rather stay together than be dispersed, so they accumulate at a certain point. These particles are not soluble inside a melt, so they are just like spit out, and they remain as a different phase on the alloy, and we see them as hard spot. Here I have a first case that I'm showing you that has all the characteristics I mentioned before. In this case, we have osmium, iridium, and ruthenium. It is very common when we have osmium hard spots to see them alongside with iridium and ruthenium. As I said, they're also both a part of the platinoid metal group. In this case, we were actually trying to discern the cause of the problem. After investigating, we found out that the gold that was being used was a 3.9. That means 99.9% gold. And of course, that 0.01% that we were not sure what it was about was containing all these impurities. Another case of contamination that we can have is when we have the use of tools. Differently from the first case where we could have the issue also when we were using fresh metal. In this case, we can only have the problem when we're using scraps because the scraps are the ones that are in contact with the tools. They tend to have a very reduced size and they tend to form clusters. Here you have an example in which we have both the first and the second case. We have here osmium, iridium, and ruthenium, which means we have contamination from gold. But as you can see, we also have iron and tungsten. These are Watts cases. So they were basically processed with the CNC tools, and the scraps remain at the end of the process were being reused, and the scraps were contaminated. And we were actually inserting residuals of the tools inside a new alloy. Third case that we can have, also in this case, we have a contamination from iron. It is very common when we use a continuous casting that we have the bar that is made out of iron, and if we don't eliminate the part that comes in contact, we have many diffusive mechanisms that take place at very elevated temperatures, such as the ones of casting, and this contamination of iron was actually coming out of it. So we have to be very careful where our metal has been and what are the elements it has been in contact with in order to actually determine the possible pollutants that we can have. Another case that we can have out of impurities comes from crucible stoppers or any type of material that we can use during the melt. In this case, they tend to be very round. You'll see they're actually almost a perfect circle. They come in clusters, so you won't see one, you won't see many, many of them. They tend to be quite big, can be present even if we use fresh alloy, and it happens more often in nickel alloys, but doesn't mean that it cannot happen with other elements as well. So Here, as you can see, we have a nickel alloy containing nickel and silicon. The hard spot that you're seeing, as you can see, is very round, very perfect. Why does this happen? Nickel and silicon are two elements that are very common together. However, there are some metallurgical ratios that we have to keep in mind while using them together inside the alloy, because if we don't respect them, we might have problems. What happened here is that here at ProGold, we always use graphite crucibles to produce, and we have tested all the products that we sent out here in our laboratory, and we didn't have any issues. And at some point, a client came forward and said, okay, look, I'm having this issue. And we started investigating, and it turned out that this person was using silicon carbide crucibles. The silicon carbide was releasing silicon inside the alloy, and we were actually increasing the quantity of silicon inside. At a certain amount, the silicon decided that it was better to react with this nickel and form this nickel silicure compound that you're seeing here, instead of remaining dispersed inside the melted alloy and do the function that it was set to do. We can also have contamination from other alloys, not only from crucibles. In this case, you also have very rounded shape and they come in clusters. Also, in this case, nickel alloys are usually affected, and it can happen even in the presence of fresh metal. Why does this happen? Well, here we can have like three main cases where we can have it. The first one is because we are not using different crucibles for different alloys. Even if we think that our crucible or die, our whole set that we're using for melting is clean, there's always some traces of the elements that we melted before that remain inside the material. And when we heat up, we actually favor some mechanisms that tend to put these old elements inside the new elements, even if we're starting with fresh metal. Another reason is because we might mixing together two alloys, either new alloys because we have them in stock and we want to get rid of them, or because we have pieces from an old process that we are not selling anymore because they have any issue. I don't know, they are not perfect and they have a different composition. So by mixing these two, we can have reactions that we do not know about. In this case, we have a nickel alloy in eating carrot, and the person that was using it actually was mixing with other pieces that had similar composition, but the other alloy had cobalt in it, which is a grain refiner, and the cobalt decided to react with nickel and silicon instead of just remaining as a grain refiner, because due to a series of thermodynamical considerations. The last case I'm going to talk about that relates to impurities is when we have deliberate pollution. In this case, we have a characteristic similar to the ones before. They're round. They tend to, size depends on how much we have polluted the alloy, and it can also happen in the presence of fresh metal. Here I give you a case. In this case, we have a reaction between cobalt and silicon, and what happened here is that the person who was doing these pieces was trying to harden, but they were not reaching the desired hardness that they wanted, so they thought, okay, I have cobalt at home. Let's add cobalt because I know I can reach a higher hardness. But they didn't know what was inside the alloy, or they didn't know what reactions could happen by adding this. They just knew cobalt could harden, and in fact, what happened is that we ended up having this reaction that you see on the picture, which was very visible at naked eye. The second case I'm going to talk about, which is the second macro category, is hard spot caused by agglomeration. In this case, they tend to be regular and rounded. They are made up basically from elements that are already inside the alloy and tend to be very small, but they appear in clusters, so the cluster area can be very big. And in this case, we can only have them when we reuse the metal. So how does this hard spots form? In this case, we have that when we start with certain alloy, we know the initial composition. But the more we use it, the more we're going to modify the composition of this alloy. Just think of something that has a lot of zinc in it. the more you melt it, the more the zinc is going to evaporate. But as things evaporate and its quantity goes low, it means that we are enriching the metal. It means that we are enriching the metal with some other elements. And as I said before, when we have an alloy, we have to respect certain ratios in order not to have undesired reactions. So if we use an alloy that has been used many times and we're enriching it in certain elements, at some point these elements might react among each other. And initially, we are going to see what is happening to our left, these needle-like shapes that they do not give a lot of problem. But if we keep on reusing this, the needle-shaped forms are going to enlarge themselves and they're going to become what we have on the right picture. So here is an example. In this case, we have hard spots made of iridium and silicon. As you may know, iridium is a common grain refiner that we define in alloys. It's very difficult to put it together with silicon. We have to respect a lot of rules. So in this case, we had a change of composition due to the reutilization of the alloy, and at some point, the quantities that we had inside were not good enough. So we ended up having the reaction between these two elements. In this case, we have a similar case to the one I told you about when we were talking about the crucibles, which is a nickel and silicon. Also in this case, the reaction was not due to the fact that we were using the wrong crucible or we were using the wrong materials for casting. It was due to the fact that we were enriching this alloy in nickel and silicon, and at some point they decided to react among themselves. The third macro category that I'm going to talk about is hard spots caused by segregation. In this case, they're rounded. They're very similar to the case before. They also form in clusters, but the origin is due to inhomogeneity inside the alloy. Let it be macro or micro inhomogeneity. I know that these two terms might be a difficult, not micro inhomogeneity might not, but micro inhomogeneity can be difficult to understand because in the first case, we only need to think like oil and water. There are two things that you put together, but they do not mix. In the second case, it is more difficult to understand, and the best example that I can come up with, it's a cake if you have ever baked. Like you put all the ingredients together and you have the dough that seems like it's mixed all together, but when you pour it into the mold, you realize that the container where you were mixing it in some areas has more flour or has more butter, and well, it was all mixed together, you couldn't see it and you thought that everything was well mixed. So also in this case, similar to the first one in the sense that we have the solid material already inside a melt, because it usually comes from whatever it is inside the material, and it's not melting during the production of the jewels. And they tend to agglomerate, like they tend to go together, and at some point they segregate from the phase they're in because they're not soluble in the melt. Here I'm going to show you the first case, which is a very, very typical case in continuous casting. In this case, when we have the rod, that we're pulling the rod down, and we're melting on top, here we have a very slow process, and we're just actually pulling down the rod, and we're having solidification rates that are different at every point of the process. I do want to remind you that continuous casting is not a machine, the machine for continuous casting is not a machine made to melt. So here, if we are not careful, we're going to have the segregation of elements, and in some parts we're going to have a certain composition that is different from the composition of the other part. This is why we usually recommend that you do a pre-melting before using this continuous casting, and even if you do a pre-melting, you try to keep mix the melt while you're doing this particular process. In this case, we have hard spots made out of ruthenium. As I said, this is also a typical grain refiner. that was not mixed well enough inside a melt, and at some point they segregated, and because they were not soluble in the gold. In this case, we have the micro inhomogeneity, as in this is also made out of an element that was already inside the alloy. In this case, we had like a very specific section. Let's imagine that you have the whole bath, and then you start like cutting small cubes of the bath, if it makes any sense. And at some of the small cubes that you have, in that specific cube, you were not mixing enough. So in that specific point, the iridium that was inside was not solubilized, because maybe in another cube, in another part, there was not enough iridium because it was not mixed well together. So in that point, we have that the hard spot came out due to solubility issues. This is the last case regarding hard spots, and I'm going to pass now to the next case, which are inclusions. So as I said before, there are different types of inclusions, but in this presentation, I'm going to limit myself to the explanation of abrasive inclusions, because those are the only one that can be confused with hard spots. All the other three categories are probably going to be explained in other webinars, and they have very characteristic causes, and but they cannot be confounded easily with hard spots. So we're going to leave that topic for another time. So how do these inclusions present themselves? They tend to be very regular and angular in shape, and they usually happen when we have very big flat surfaces. And of course, as it comes from the abrasive that we're using to polish the material, it can happen even if we're using completely fresh material. I must remind you that differently from hard spot, that is something that happens during the melting of the pieces of the metal. In this case, the pieces are okay after melting, and the defect is caused only during the finishing treatment. What we have is what I explained before. We have a base that is very soft, and we have a particle that is very hard, and when we use that particle to try to polish, it remains trapped on the surface, and while we try to push it with the brushes, it just pushes forward the metal that it has underneath it, leaving the void behind. In this case, I'm going to show you inclusions. One moment, please. I'm sorry, I don't know why the image is not. Sparita l'immagine. Well, I'm sorry. There was an image that I don't know for what reason it's not showing. But we have aluminum oxide that is a very typical. No, è la precedente, quella c'è stata. They're the aluminum oxide, which is a very typical abrasive that it's being used. We had, when we put the version online, I'm going to add the image, I'm sorry. If you could see it, you would see like they're very angular shaped. They tend to come in big spots because abrasive particles tend to stick together. Here I have another case. In this case, we have silicon, iron, and chromium. Oxides from these abrasives are very common use. And if they release, it means that most probably the abrasives are defective, or they tend to be old. So we also have to be aware of this thing, that if we use old material, it might cause problems. As I explained initially, one second, please.
Oh, sorry, everybody. It looks that we have some problem with the sharing of the presentation, and we ask you to be patient for a while, and we try to recheck. Maybe we can restart the presentation. So we hope to be able to restart in a few seconds. Be patient, please. So this is not an hard spot, eh? We have a person that is trying to relaunch the presentation. Maybe we can restart. Gisela, are you okay now? Oh, the microphone switch on. Okay.
Sorry
You can go. Sorry.
for the issue. We had problem with the computer. Actually, I'm going to show you the previous slide. This is the picture I was talking to you about. As you can see, they're very angular shapes and they're very irregular. Sorry again for all the problems with the computer. So turning to what we're now, how do they form? As I said, it is very common for this type of inclusion to occur when we have very big and flat surfaces. Even if we have a hard material, as you can imagine, if we have available the surface that we see on the right picture, it's not a lot that this hard particle can move along the surface. Instead, if we find ourselves in the situation of the first picture, imagine that that you have the inclusion at the former left part of the surface. It's going to move along the whole thing until it reaches basically the end of the ring. So now, as I have finished this small summary regarding hard spots and inclusions, I'm going to give you some suggestions. I'm going to remind you some of the most important things that I've said in this webinar. And it is, I ask you to be very careful about what type of materials you buy, because sometimes pollutants come from materials and the quality of it is very important. We have here many times people saying we have hard spots, and then we find out that due to cost, due to the process that they use, because they do it internally, they tend to have gold that is not exactly the highest quality. We also suggest that you avoid adding elements, or that if you can, try not to play and make your own master alloys. If we are here, it's for a reason. We have studied this. And there's a whole science behind this. If you start adding all the elements that come to mind, you might get lucky at some point, but you also might get very unlucky and have a lot of problems. Please keep in mind that it's very important to have different crucibles for every process. If you are using an alloy or two different alloys that you're completely certain they have the same elements, you can think about reusing them. But if you have not the certainty that they have the same element, or that they may have contaminants or pollutants from other processes, it is better to keep things separated. Please, it's very important to use the prime melting, especially in continuous casting, because it's very, very easy to have hard spots in such a process. And please be careful about grain refiners. There can be a very helpful thing, but if not used properly, they can also give you a lot of problems if you don't know what you're doing. With this, I conclude this presentation, and I thank you everybody for following me and for giving us your attention this afternoon.
Thank you very much, Gisela. As usual, okay, we leave in this last slide our email addresses where you can write wherever you want. We are at your disposal anytime to answer and go deeper in some topic if you didn't understand something or if you want to clarify, okay? In this moment, there are no many questions, so I invite you, if you are curious, if you have any doubt, okay, to write us, and we will be happy to answer you, okay? So we can start with the first one, Gisela, which is from Artec. Can a particular raw material used in different grades of graphite crucible lead to hard spot? This is the first question.
Let's say that graphite tends to be the best material to cast any piece of fuel. Of course, the quality of graphite depends not because of the hard spots, because if you use a bad quality of graphite, these might release into the melt and you're going to end up with graphite inclusions, which is another type of inclusions I talked about before, I mentioned before. Whether these inclusions happen or not, it's not dependent of the quality of the raw material or which raw material you're using. It's actually dependent on the grade and the quality of the graphite itself and how many times you have used that graphite.
Okay, thank you. Jay Garcia, okay, is asking is there any way to coat the crucible so that is where is low? I don't well understand. You understand the questions,
No, could
Gisela?
you please repeat it?
So if there's any way to coat the crucible.
I think that if I understand correctly, I hope, is that you're asking if there's any way to remove part of the crucible so we can reuse it. If this is the question, if I'm getting this right, no, there's not, because graphite, it has an inherent porosity to it, and when we melt, we're talking about over 1,000 degrees, so we have a diffusion phenomena inside, and elements are bound to migrate inside the porous material of the graphite, and when we reheat it again, just as they went in, they're going to come out. So you basically would have to, you know, cut the thing in half every time. It's not like you can remove the most superficial part and reuse it. I would highly not recommend it.
Also, there is another question which is quite general, okay? Is asking, I try to summarize, asking you, what are the general reason getting the hard spot? The general, yes, general reason why you can get hard spot generally. It's quite general.
As I said, the reasons why you might get hard spots is because you're using low purity raw material, especially gold, and because you are not, because you are reusing your scraps a lot. I do understand that it's not impossible, it's not feasible to use the gold one time only and then start with fresh material, but we have to limit how much we reuse the scraps and the quantity that we reuse every time. It is better to keep always the amount of fresh material higher than the scraps. Also, the quality of the machines that we use, of the crucibles that we use, is going to influence. As I said, all stuff, all materials are going to give you more problems than things that are new. So you also have to check your tools, your abrasives, your crucibles every now and then and make sure they are in perfect state.
So it looks, Gisela, that there are no more questions. Okay. Okay, sorry. There's a new one from Mr. Azar. How do you treat the scrap before using it again for casting?
Now, it depends on where the scrap comes from. If the scraps come from CNC machining, I do recommend that you avoid using it, because some of the iron, tungsten, or whatever material is on the tools is bound to get inside the scraps, and risk of hard spots is very high. But even if you do, I recommend that you wash them thoroughly to eliminate any dirt that it is inside. This also apply in the case of casting. Be mindful of the pieces, that they do not have residues of investment, that they are very clean, that there's no presence of oxides on the top. And as I said, limit the use of them. If you really have to do it, try to do at least 70% fresh material every time. And after, let's say, from 6 to 8 times, and for me that's a lot already, try to just send to refining all the scraps that you have and start from a fresh, because it's just a second to get hard spots. And the problem with having them is you cannot remelt the pieces that have hard spots. This is something that I forgot to say before. As I said, hard spots come from elements that do not melt at the typical UV reprocesses temperatures. So even if you take a piece with a hard spot and you put it again inside a melt, you're just getting the same hard spot again, because the temperatures that you're using are not enough to melt that compound that has formed. We have to go over 2000 degrees in order to get rid of it. So the only way to separate it and just get rid of the hard spot is to refine it.
Okay, so okay, the question is slowly arriving. So I would like, in any case, to remind you that, as I told you, we are gonna having also every Thursday our webinar. In the next one, the topic will be the characterization of the 80K gold alloys, which is important talking about, because it's important to get precious information for selecting the most suitable composition for each process. So please register also in the next one, which is arriving next Thursday, okay? So let me try to tell you, Gisela, the next one. So Stefanos is asking, there are many types of alloys. When you mention about using different crucible for different alloys, it would be very costly if we use different crucible for every alloy. What are the particular elements in the alloy that should take in consideration to decide whether we can use the same crucible or we need to use different one?
Okay, I know that it can be costly. In the case you cannot, like, the least you should do in any case, it is at least try to keep one crucible per color per carriage. So that way it's easier to handle, because let's say that the chances of two 18-karat jello alloys being compatible are higher than maybe a white alloy in 18-karat with a jello alloy in 18-karat. So try to keep colors and carriages separated, and if possible, try also to keep separated in the case you know that it has grain refiner or the oxidant, because not all grain refiners can be used on all carriages or in all alloys due to all the elements that go inside. So at least by doing this small distinction, you can already have like good chances of not getting this problem. Of course, if you know, even if you don't know the exact quantities, but you know the elements that are inside the alloy, you can also separate it by elements. So if you know that a given alloy has always, let's say, silver, gold, zinc, and iridium, any alloy that contains all those four elements can be casted in the same crucible, because you're not having contamination. When you reuse the crucibles, you're not going to change a lot the composition of what you have there, unless you're inserting a new element.
Okay, thank you. Mr. Chintin is asking, in case we get hotspot in investment casting pieces, in that case, is it advisable to refine the total metal, or can we remelt it and then cast again? What you suggest?
Now, for every piece that you confirm you have hard spots, you have to refine it. If you want to remelt the rest of the metal just to make sure that nothing is there, you can do it. But as I said before, if you see a hard spot and you remelt it, the same hard spot is going to come again in the next melt, just in another place. So you're just changing the position of the hard spot because you cannot remelt it. Once it has formed, it is there. Also, once it has formed, the chances of it getting bigger is also high. So if you remelt it, chances are that the next time that you have the hard spot, it's going to be bigger than the first one you found.
Okay, Mr. Debashish is asking, what about iron contamination for casted jewelry? How does it happen?
Now, in iron, it's not commonly used in casting processes. There are some rare cases in which it's used as grain refiner, but it's very uncommon. If it comes from casting, it means that the piece, for any reason, has been either treated with tools, or you have remelted scraps that have not been cleaned properly from abrasives. As I said before, iron oxide is a typical abrasive. If you have an inclusion from it and in the pieces, and you remelt it again, and you're putting it in the inside the new melt, it's bound to react with something. Let's say the advantage of having inclusions of abrasives is that you can remove it. If you find the right material, of course you're going to lose gold, and you might, because you have to remove the whole layer. But if you remove it, unless you have to have a specific dimension of the pieces, you can kind of recuperate it, and you can reuse it, because you only have to remove that layer. So iron probably comes from abrasives that have not been cleaned properly from previous scraps.
Yeah, Alexis is asking if you can come back at the presentation in the last slide. He said that second point, okay, if you can check, Gisela, is not so clear for him. If you can better explain
Avoid
him.
using single elements to prepare gold or silver alloys. Okay, so this refers to the case in which we go and modify the alloy, as I explained in the case of this person adding cobalt just to harden the pieces. So avoid it, because if you don't know what's inside or the quantities of what it is inside, you might get reactions you do not want. And it also refers to be careful when you mix up your own alloys. If you put gold and silver together, you're not going to get more problems. But if you start to get creative and adding all the elements on the periodic table, things might happen. There's a lot of science behind metallurgy. There's a lot of equilibrium that have to be respected. And the more elements we add into the mix, actually, the more difficult it is to foresee what's going to happen. When we have 2 or 3 elements, it can be kind of straightforward. The more elements we add, and it's very common to have more than 3 elements, the more complicated it actually becomes to foresee what's going to happen. So unless you don't have the skills or the preparation to know what's going on with these metals, chances are that by playing little chemist is going to give you bad results.
Okay, Mr. Maish is asking if we have any suggestion for the best graphite grade.
Yeah, the best graphite grade is isostatic graphite.
Okay, Mr. Nilesh is asking if we got hard spot on the jewelry, how can we remove it without melting? Is it possible? Is there any way to do it?
No, once you have it, you have it. You cannot get rid of it. You could try to see if you can remove the whole layer, but usually when these compounds form, they actually go also in depth. So it's, imagine like you have a rock on the beach, and maybe half is on the water and half is on top. Even if you start removing the part that it is on top, at some point you might see what's underneath, and you will have to go deeper. And at that point, it's too time consuming, And what are you going to spend trying to do that is going to be not convenient. It's easier just to send it straight to refining.
Okay, Marcus is willing to know, while during investment casting, you think it will help if we go about 40 to 50 Celsius degrees over the actual casting temperature and then come down to actual casting temperature and then cast. Will this reduce the possibility to have hard spot, you think?
Now, the reason why we suggest to go over and then come down, it is because the higher we go with temperature, the better we're going to homogenize our melt. The problem is that investment, if you have investment casting, the investment reacts over certain temperatures. So if our metal is too hot, when it touches the investment, it's going to generate a series of reactions that are not going to generate hard spots, but are going to generate other issues. So we have to find a compromise in order to have a good mixing, but at the same time to avoid these problems with investment, the composition. So we go high to mix, and once we are convinced that the thing is mixed well, we go down with temperature to limit the reaction due to temperature when the metal comes in contact with the flask.
Okay, there's the last question. If the casting is at rest for a long time, does it lose properties or suffer any kind of deterioration?
It's a difficult question. It also depends on the conditions of the casting. Of course, if you have an alloy that has a lot of zinc, for example, the longer it is melted, the higher the chances that the zinc is going to evaporate. But let's suppose that you have an alloy that has a little bit of zinc, but has a lot of copper, a typical 18-karat red gold alloy. It also depends on the conditions of the casting, because if you have an open casting machine, the melt is going to react with oxygen, and the higher the temperature, the more favorable the reaction with oxygen will be. So you leave it longer, the more oxides that you're going to get inside. If you know that you have a closed machine, that the bath is protected with argon or nitrogen, chances are that you can leave it longer. But you have to take into account that also keeping the melt for a long time, even if it's protected, it means that you're spending more in gases, in protective gases, and you're spending also more in energy just to keep the bath heated up. Yeah, after a certain point, if you don't have the right conditions, it would be a moot point because you would be wasting just resources.
Okay, Mr. Vagesan is asking if does the hard spot even depend to some extent on the type of casting process?
No, in the case of unless we are not considering continuous casting, in which there are some big chances, if things are not done correctly, that this may happen. If we are talking about like regular casting, no, we don't have this issue.
Okay. Okay, Mr. Artek, does casting alloy with too high deoxidizer can develop more hard spot? So is there any connection?
One, it depends on the oxidizer that we're using, because there are many elements that do the same work, and not all the elements react in the same way. It also depends on the other elements that we have inside the alloy. Of course, if we have, for example, it's very common in nickel alloys, because nickel alloys tend to have a lot of zinc in it, and they tend to have silicon, as in the cases that I explained. So if you reuse it a lot, of course, zinc is going to evaporate, and if you already have a considerable quantity of the oxidant, it's going to become even higher because you're losing some other element. But If you find yourself in a situation where the antioxidant does not react with any of the other elements that are present in the melt, the risk is not going to be higher. So there's not a general answer for this question. We have to look case by case. Of course, if you have any specific case that you want to ask about, feel free to send me an email. I'll be glad to explain for very specific cases if you want to go into detail.
So is there the possibility to have hotspot is depending if we use different kind of casting machine. If we have, let's say, closed system or hand pour machine, is there connection in front to the risk having or no hotspot?
If you have an open machine, the risk of having hard spot is not going to be higher than in a closed machine if all the rest of the things are the same. Of course, if you start adding variables, like you start having more scraps, or you're not cleaning them properly, or if you're using a low quality of gold, it's going to happen whether you have an open machine, a closed machine, continuous casting machine, because it depends on other things. Of course, if you have an open machine, you may get another series of issues because you're not protecting the melt, and you end up having oxide inclusions instead of hard spot. And also those ones they're difficult to remove. It's better to avoid them. If you can, please try to protect the melt, because you're going to get better results if you do that.
Okay, it looks that that's all. Okay, there are no more questions. And so I think that if nobody wants to go ahead giving other questions to Gisela, we can stop here. Remembering you, as I told you already, that we are gonna organizing next Thursday the other new webinar where we will talk about the characterization of the 18K gold alloys. So I ask you, please to register and be present also next week. I would like to give you a special thanks, okay, to attend today at this webinar, and giving also a thanks to Gisela. So we can close here, I think, and give you appointment next weekend, Thursday, 4 p.m. chat. Okay, thank you very much. Thank you to everybody, and see you. Thank you. Bye-bye.
Thank you.
Bye.
Goodbye.